For question 2 on your homework, you're going to be looking at a couple of statements and judging whether they're true or false. So, and they're all based on if an electron is excited from the ground state to an n equals to 5 transition state in a hydrogen atom. So your first statement reads, if it takes less energy to ionize the electron from the n equals to 5 state than from the ground state. So one way you can approach this statement is to look at the Bohr equation for the hydrogen atom. And since this number here is a constant, you can ignore that. And since the final transition state is essentially going to infinity because you're ionizing the electron, you can cross out this term and just look at this term right here, the 1 over ni squared, in order to determine how it changes energy. So there are two different scenarios you're considering if you're starting from the n equals 5 state and the ground state. So I have plugged in my states here. This is my ground state here, and this is my n equals 5 state here. And we can tell that the ground state value is going to be bigger than 1 over 5 squared. So if we plug that back into the equation, you're going to get a much larger change in energy for 1 over 1 squared than 1 over 5 squared. So if that's the case, then it does take less energy to ionize the electron from the n equals to 5 state than from the ground state. So let's take a look at another statement. Here it says the wavelength of light emitted if the electron drops from n equals to 5 to n equals to 4 will be shorter than the wavelength of light emitted when the electron falls from n equals to 5 to n equals to 3. So let's take a look at an equation we can use to determine or to compare energy and wavelength. So we have this, and we have this, and we combine them, we can get E equals to hc over lambda, and we take out h and c, which we know are constants. We can see that energy is related to lambda inversely. So let's take a look and see how that applies in the Bohr equation. So again, looking at the Bohr equation here, you can see that you have your end final and initial states, and if we again ignore the constant here and we just compare this term between the two different transition states that we have, we can figure out that the transition from the 5 to 3 state gives you a bigger value than if you transition from the 5 to 4. So because your energy will be correspondingly similar, and we know that energy is proportional to 1 over lambda, we can determine that the transition from n equals to 5 to n equals to 4 is less than that of from n equals to 5 to n equals to 3. So the smaller the energy, you'll have a longer wavelength, so the statement is false. Moving on, let's see if energy is absorbed and if it is the same as the energy emitted if you're going between 1 to 5 or 5 to 1. So again, we can look at it in terms of the equation, and we can just look at the terms here, which I wrote out here. So you can see that they're going to be equivalent to each other. Both of these are going to get you the same values, and I've just put an absolute value sign here because we're not looking at the signs. The signs only will indicate whether or not the energy is being emitted or absorbed. So if you don't believe me using numbers, we can also take a look at the graphic. So if you're absorbing from the n equals to 1 to n equals to 5, you have your transition arrow here. But if you're emitting energy from n equals to 5 to n equals to 1, this down arrow here is shown. As you can see, these two arrows have the same magnitude, so we know the statement is true. Moving on, for n equals to 5, the electron is in an excited state. So an excited state is anything that's not the ground state, and the ground state is always n equals to 1. So this statement is true. And finally, we have the electron is closer to the nucleus on average in the n equal 5 state than in the n=1 state. So yes, that is not true, because that is false, because being closer to the ground state means it's closer to the nucleus.